I'm Alan Papalia, and I'm here to talk about SCORE, a new initialization approach for range-aided SLAM problems. I was lucky to work on this with Joseph Morales, Kevin Doherty, David Rosen, and John Leonard. Before I dive into that, let me define range-aided SLAM. Let's consider pose graph SLAM, in which we have variables that are either poses or landmarks, and measurements are relative rigid transformations between variables. Range-aided SLAM is the extension of pose graph SLAM to include range measurements, that is, point-to-point distance measurements between variables. One reason for the potential of range-aided SLAM are the ranging capabilities in everyday devices. These are things such as modern cell phones, which are being equipped with ultra-wideband chips, or even Wi-Fi access points. Each of these devices can obtain time-of-flight range measurements. Additionally, range-aided navigation poses substantial benefits in a wide range of robotic applications. This can be evidenced by the increased use of ultra-wideband ranging on drone platforms and the common usage of acoustic ranging in marine navigation. So this begs the question, why don't we see range-aided SLAM everywhere? Well, there's maybe a few reasons. The one we're going to discuss today is effectively that non-convex optimization is hard. Specifically, most modern SLAM systems utilize local optimization to solve non-convex optimization problems. As a result, the quality of the state estimates we return from most SLAM systems are highly dependent on having a quality initialization to these non-convex problems. Now at this point, an astute listener might go ahead and ask the question, is this really a problem? Aren't we used to using non-convex optimization everywhere in robotics? And to be honest, largely, they'd be correct. This is an area where range-aided SLAM begins to differentiate itself. The range measurements themselves actually become part of the challenge, and that the range measurements induce additional non-convexity into the underlying optimization problem. To demonstrate these challenges, I've drawn up a simple 2D simulated experiment as seen here. Here, the blue lines represent the trajectory the robot followed. The red star in the upper right represents a landmark. So at each time step, the robot obtained an odometry measurement, and every few time steps, the robot also obtained range measurements to the landmark. What we see here is the result of a local optimizer initialized with a standard odometry-based approach. The optimizer appears to have gotten stuck in a local minima, which resulted in this distorted trajectory estimate that poorly represents the trajectory the robot actually followed. Having observed these issues, this brings us to SCORE, an approach to provide principled initializations to range-aided SLAM problems. I like to think of SCORE as a type of funnel that takes all these different arbitrary initializations and encourages them towards the basin of convergence for our global minimum. To get a little more into the technical details, SCORE is built on convex optimization, and as a result, any solutions to the SCORE problem are globally optimal, regardless of the initializations provided. Because it's built on convex optimization, SCORE is highly scalable, and we demonstrate its usage on problems of over 5,000 poses. And in a note of theoretical interest, SCORE is actually directly derived from the maximum a posteriori estimate for range-aided SLAM. So let's dig into SCORE a little more. How do we actually arrive at SCORE? So it all begins with the MAP estimate, which is actually a non-convex, nonlinear least squares problem. We reformulate this problem to shift all of the non-convexity in it to the constraints. We then perform various modifications to these constraints to remove their non-convexity, and the resulting formulation is what we term SCORE, which is a convex relaxation of the original maximum a posteriori problem. Notably, SCORE is a second-order cone program, a special class of convex problems that can be solved more efficiently. For more mathematical details on how we actually derive SCORE, we refer you to our paper. We've now described how we arrive at the second-order cone program, but we haven't actually described what we do with it. Our initialization approach begins by solving the second-order cone program, given any arbitrary initialization. We then take the solution from this second-order cone program, project it to the feasible set of our original non-convex, nonlinear least squares problem, and then we use a local optimizer to refine this projected estimate. Now that we've explained at a high level what SCORE is and how it's used, let's look at it in practice. Here's a simulated 20-robot experiment, where each robot has its own odometry and there are range measurements between the various robots. As we see, SCORE is able to untangle this arbitrarily bad initialization we provide and reshape it into something which qualitatively matches the gridded trajectories we expect. This experiment shows that SCORE is capable of handling large and fairly complex problems which may not have had appropriate initialization procedures before. Beyond simulations, we also tested SCORE on a set of real-world experiments. These experiments consisted of a single autonomous underwater vehicle and 4 acoustic beacons. Inertial odometry and acoustic ranging to the beacons were used to estimate the robot's trajectory. We compared SCORE to an odometry-based initialization procedure by locally optimizing the given initialization and evaluating the corresponding estimates. As can be seen, the estimate obtained from the SCORE initialization consistently had lower error than the odometry initialized estimate. These results suggest that SCORE has a practical place in real-world range-aided SLAM problems. Hopefully now you've seen enough that SCORE has caught your attention. We've released the code for SCORE as open source on GitHub, and we encourage anyone interested to try it out.